It's like, man, like I remember last year, it was so much shorter than this year because we keep going faster and faster as we rotate around the sun, right? No, it's kind of boring. Like every year has pretty much the same length of time, right? Yeah, like that's how we set up the notion of time in antiquity, right? Through the regular celestial motion of bodies, whatever. But so yeah, there is no tangential acceleration is my point, only radial. And so where is that coming from? It's gravity. So G, mass of the Earth, mass of the Sun, divided by R squared, right? All right. Well, I started out with the Earth, but apparently it doesn't matter. And what we got is we got V squared is equal to G times the mass of the Sun divided by, looks like R, right? How fast are we going around the Sun right now? How long, let me ask you a different question. How long does it take us to go around the Sun? 365.25 days, yes, very good. A year, right? Now, this distance, it has a special name. Oh man, I can't remember what it is. Yeah, is it an astronomical unit? R is equal to 1 AU? Yeah, okay. Yes, we did, and it is for our convenience. It is what? It's okay.
Everything else is pretty much relative to us.
So, in terms of astronomical units and years, you have that V is equal to what? 1 astronomical unit per year, right? For the Earth. Not true for other planets, right? Great. Now, forget about the Earth for a second here. So the velocity really is what? It's 2 pi times the radius of whatever planet we're talking about, really, divided by the period of the planet, right? We use a p for planet. That quantity squared is equal to G, mass of the Sun. Because I'm pointing out that really, while I started with the Earth, we could just as well have done Jupiter or Mercury or Mars or that thing we don't know the name of out in the Kuiper Belt. Although I guess that's a highly elliptical orbit or something. I don't know. People speculate. And then you solve this thing, right? What do we get? We got ourselves a 4 pi squared radius of the planet cubed divided by the period of the planet squared is equal to G times the mass of the Sun. Let's clean this up a little bit. So what this says is the radius of the planet cubed divided by the period of the planet squared is equal to G times the mass of the Sun divided by 4 pi squared. Did you guys know what this is? First name, Johannes. Kepler, yes, this is one of Kepler's laws. It states that the cube of the basically radius of the orbit divided by the square of the period of the orbit is a constant. Now, Kepler didn't say that the constant was G, mass of the Sun, divided by 4 pi r squared. That's something that we only later derived once Newton posited that the force of gravity was inversely reciprocal to the distance between the attracting bodies. Right? Kepler just looked at a bunch of data, tried really hard to fit it to these Platonic solids, failed, and was forced into these ignoble elliptical orbits, much to his annoyance. Because these are not perfect circles. You know. That was a Copernican. Before people the epicycles, circles upon circles upon circles. No, it's ellipses. Now, let me show you the beauty of the astronomical unit is it allows for very lazy calculation. So if you have a mystery planet at 2 times the Earth radius, All right. Then, how long's a year? So this is a year on planet P. Period of its orbit. So what you do is you just set the radius of planet P cubed divided by the period of planet P squared equal to the radius of Earth cubed divided by the time of Earth squared. What is this in terms of astronomical units and years?
One.
This is 1, yes, very good. I mean, technically, astronomical unit cubed divided by year squared, fine. And so what's the the TP? TP would be the square root of RP cubed. In other words, the radius of the Earth to the 3/2 power, right? Whatever that is. Oh, I'm missing my units. I mean, it's in years. Oh, something wrong. Sorry. I did something wrong. I forgot my 2. 2, yeah, 2. 8, right? So 2 cubed is 8. 8 times, oh, so it's 8 to the 3/2, right? Because this is 1 in our current units. So yeah. Whatever that is. Can you tell me? I forgot my calculator today. All right, then I guess it remains a mystery. So we're going to work interesting problems, like we'll be able to solve, for example, how far out you have to be to have a satellite that tracks with the rotation of the Earth, right? The geosynchronous orbit problem. You know, the Earth. How long does it take the Earth to spin around its axis? 2 days. Yeah, one day, right? So then the question is, if you want an orbital period of 1 day, how far out do you have to be to get a circular orbit that does that? That's called geosynchronous orbit. We can answer that using this kind of stuff. We'll think about problems of escape velocity, and we'll also solve if you have 2 moons rotating around a center point, like how does that motion go? There's also all kinds of interesting gravity problems we can solve. So anyway, thanks guys. You can ask me some questions about your homework next time if you want.